All right, so when we left off in class, we were looking at this function s of t with a question about computing the average rate of change between t equals 3 and t equals b. That is, over an interval on the t-axis that started at 3 and ended at b. We did this was by using the slope formula. Slope formula essentially asking what's the change in s over the change in t, right? Over this interval, the t value changes from 3 to b, so b minus 3 measures that distance. And in the y direction, or s direction, this difference, s of b minus s of 3, measures that distance. So correctly, we substituted here. We said that s of b was this value. We plugged in b for t into the formula. We said that s of 3 is 5. Over here we plugged in 3 for t and computed that and saw that it's equal to 5. I told you we could simplify this a little bit, so let's do that. We can combine like terms in the numerator. Minus b squared plus 2b plus 8 minus 5 is plus 3. And maybe you recognize that we could go even a little further by factoring. Maybe we'll save that for later. So let's move down to part B. Part B, on one hand, is asking a very similar question. We are looking at the same formula, same function, s of t. It's an interval that starts at t equals 3, but this time, instead of ending at b, I am telling you the length of that interval. So if you're paying attention, if the length of that interval is h, that is our delta t, the change in the t value from the start to the end of that interval. And the average rate of change really is the same as above. It's a change in s over a change in t. And, well, given what we just said, that change in t is just h. Right, can you see why that's true? But what about the change in s? We know that s value, when we plug in t equals 3, is s of 3, right, when we found that above to be 5. But what do we plug in here to get that value? Well, we're on a number line. We're starting at 3, and we're moving ahead h units. So what we get there, 3 plus h. So we want to know what's the difference between the y values, the s values at those points. We have s of 3 plus h minus s of 3. We know that s of 3 is 5. We found that above. What is s of 3 plus h? Oh, we have to be a little careful here. But we know what s does. Let's just plug in that whole quantity, 3 plus h, everywhere we see a t in this formula for s of t. So s of 3 plus h, that is minus 3 plus h squared plus 2 times 3 plus h plus 8. And we can distribute and collect like terms. We end up with minus h squared minus 4h plus 5. Put that in here for s of 3 plus h. And when we simplify, our average rate of change is given by the formula minus h squared minus 4h all over h, because the 5s will cancel. On to the next page. I want to review what we said about average rates of change and then connect that to a new topic, an instantaneous rate of change. So to start, what do we know about an average rate of change? 1, this takes place over an interval. Specifically, it's an interval in the domain of our function. Maybe from A to B, and the distance between A and B, oops, that's our delta x, or we've called that h. Graphically, we could think of this as the slope of a secant line. Remember, a secant line is a line between 2 points on our graph. So we could draw the line, we could draw the points on the graph corresponding to x equals a and x equals b, and connect those with a secant line. And the average rate of change is the slope of that line. Algebraically, we use the slope formula. Change in y over change in x. That's f of b minus f of a over b minus a. Or, as we saw in part b above, f of a plus h minus f of a over h, if our interval starts at a and goes to some point h units later. So then what's the business about an instantaneous rate of change? Well, the big difference is instantaneous rate of change occurs at a point in the domain. Maybe the point is just A. Graphically, we can think of this as a slope of a line, but it's a slope of a tangent line. What's a tangent line? Well, it's a line that touches our graph at one point and follows the contours, or sometimes it's helpful to imagine that our 2 points for a secant line are really close together, and we are drawing a line that goes between them. So we can draw the point corresponding to A, and maybe imagine there's a second point really close to it, and if we were going to attach those 2 points of the line, our tangent line would look like this. And the instantaneous rate of change at that point is the slope of that tangent line. Algebraically, how do we do this? Well, kind of like what I just said. If we imagine a secant line going through 2 points that are really close together, that's the idea. What's the corresponding thing to do if we're thinking about an interval of length h? Well, h is the distance between the 2 points. So if we're closing the interval, we want to let h get close to 0. And this getting really close business, we'll see that in the next section. So this last page is all about instantaneous rates of change, which we know we could think of as the slope of a tangent line. So in number 4, when we ask about an instantaneous rate of change being positive, we really are asking, what's a point where the tangent line has a positive slope? And you might pick a point like -1, x equals -1. And if you draw a tangent line to the graph at that point, we'll all agree that that line has a positive slope. So yes, at x equals -1, positive instantaneous rate of change. You may have correctly said -2, x equals -2. Maybe you said something like x equals 5. Both of these are right. There are several right answers. What about a negative instantaneous rate of change? Well, we need a place where the tangent line has a negative slope. Maybe a place like x equals -1. I'm sorry, x equals 1. So we can draw the tangent line. Remember, our line is touching the graph at one point. We could imagine if this were 2 points really close together, this is the line that would connect the two of them and go through them. So x equals +1 is a good answer here. You could have said x equals 0 or x equals 3, and there's lots of others. Anything in between those certainly would work. And then part C, the instantaneous rate of change is equal to 0, we need a horizontal tangent line. So where do we see that? Well, maybe somewhere like the bottom of this dip. So around, I don't know, 3.75 or something. I'm not too picky about estimating it exactly. We could correctly say, likewise, the top of this hill, maybe minus 0.5. And in fact, those are the only two answers for a horizontal tangent line. That is an instantaneous rate of change equal to 0. All right, so number 5 asks us to actually estimate the slope of some tangent lines. Let's see, x equals -1, we drew this tangent line, and we can just look at that line and say maybe, oh, I don't know, it goes through this point and this point, so that's a change in y of 3 and a change in x of 2, so change in y over change in x, 3 halves. Positive 3 halves is the slope there. X equals 0. This is going to get a little busy, apologies. Something like that. And if we want to estimate that as being pretty close to a slope of -1, that looks good to me. And x equals 3, let's pick a new color here. It's down here. Extend the line so we have something to work with. And maybe let's say for a change in x of 3, there's a change in y of 1, 2, 3, 4. So let's say minus 4/3. You could take a look at those lines and check those for yourselves. Number 6, find a point on the graph where the instantaneous rate of change is -2. We see here instantaneous rate of change, and we think slope of the tangent line. So we need a place where the tangent line has a slope of -2. This one will be easier on the tablet than it will be in your notebook because I can do something clever like maybe drawing a line with a slope of -2 and then move it around to see where is it tangent. So remember, a tangent line should just touch the graph. So here maybe it looks like around x equals 2.5. That works. Let me clear this out a little bit more so you can see. And if we zoom in, sure, there is another answer. I'll leave that for you to find, but x equals 2.5 is a good answer there. And then the last question here, thinking about our answers to 3a and 3b, these are the algebraic rates of change we found. How could we use them to find instantaneous rates of change? So let's go back up to one of these. Here we found this expression with the b's, gave us the rate of change for an interval starting at 3 and going to b. And then in the last page, we said, well, we get from an average rate of change to an instantaneous rate of change by letting b get close to 3. So the question we need to answer here is, what happens to this expression when b gets close to 3? And we need some machinery to help us answer that question, and that's what's coming up in the next section of our textbook.